Hi. Hi, everyone. Thanks for joining me for the session. My name is Toni, and today I'm going to talk about immutable code in .NET. I presume that most of you are developers. Can I just get a raise of hands? How many people are developers here? It's not a shame, so it's okay. Thanks. Anybody working with F#? Kinda? Okay, excellent, because this topic is way too soft for you guys. You probably know everything, because in F# everything is immutable by default. Okay, so if you want to reach me, here's some information, but let's get started. So today's agenda is to talk a little bit about philosophy, why immutable, why now, why all the talking about that, and then I'm going to jump into C#, show how to do immutability in C#. Then I'm going to talk about a little bit about Frontend, aka the client development, and let's just mention how immutability can be done on backend, and hopefully we'll reach some kind of conclusion, which I already have, so you're just going to share with me. So let's talk about immutability. What is immutability? Immutability comes from ages ago. It's a very popular thing in functional programming languages, and C# is not by definition a functional programming language. It's a multi-paradigm, so it can be functional if you really, really squint and force it, but by default it's not. So why would we want to talk about immutability? Is there a fad around immutability? And if you look at the landscape of development technologies in the recent 10 years, there is so much development in functional space. So you have languages like F# coming into prominence. You have Scala on the Java stack. You have Elm on the front end. You have Haskell, guys at Facebook use it. You have Reason, a new language on top of OCaml. So many languages are now using functional paradigms. Immutability is one of the cornerstones of functional programming style, and we want to bring it into C#. So let's see why do we actually want to do it, especially when you consider that the computers themselves are built on von Neumann architecture, which is mutable. You basically have registers, you put stuff in, you change, voila, so it's mutable. So why would we do something that's really hard and kind of hostile? So let's consider this simplistic programming model where you want to feed chickens, because that's something you do every day, right? I mean, it's not chickens; it's basically data tables. But so bear with me for a moment. So how do you feed chickens? You basically go in and increase the value of certain property, and voila, you're done. However, how would you do it immutably? So you cannot change anything. So you get a list of chickens, and then you create a copy of a chicken with everything intact, except the stomach, which is now full. That doesn't really map to modern real world where people have text boxes, type something inside, and voila, it's changed, right? Or let's consider the typical class development style we use in C#. You have a mutable user, aka user, with two properties, and it's his birthday, and then the new value is entered for age. However, how would you do it with immutability? You would have to create a copy of a user with everything intact. In this simple case, it's just name, but you can imagine it like in the complex scenarios, you have like 40 fields, and just one is different. So you changed just one value, you created a copy because you cannot change, so basically you created a new value that's similar to the old one, right? So how would we do it in C#? You would have to jump through hoops a little bit, because if you think about it, just removing this lower part brings you to the mutable user. And for immutability, you have to make everything private, or just simply hide it completely. Like there are no setters here. If you look at the properties, there are no setters. So to change something, you create a copy, which sounds a little bit unreasonable, and it's definitely not the way C# was intended. C# didn't come with immutability in mind. Okay, so one small demo here. I will not do live coding because that always ends up badly. So I'm just gonna show a couple of things. Yeah, I haven't done sacrifice to demo gods. So you might ask yourself, like, okay, so if you have private setters, how on earth I'm gonna, for example, deserialize those things? And luckily, C# actually helps you. For example, if you're using JSON.NET, anybody here not using JSON.NET? Exactly. So if you have a simple class that has no setter, as in the name, and if you want to deserialize it from a JSON object, which is a typical thing you do every day, whether it's mobile, desktop, or web, if you want to deserialize it, you might say, like, how am I going to fill these values? Even the reflection won't help you because there is nothing to reflect here. It's kind of philosophical. So if you run this thing, come on. I cannot see .NET run. Excellent. you'll see that actually C# will help you, and it will correctly. I mean, I deserialize, then serialize again. I could have just used the original string, right? But so the point is that that languages and libraries can actually help you achieve immutability in certain cases. Okay, so how do we do immutability? It's actually a spectrum. There's not like, it's not a binary thing. It's either immutable or not. First way is like if you just agree in your team that you will never change anything, like I promise I'm going to do due diligence, this will never fly because if you can, you will try to do it, right? And also there is nothing preventing somebody else coming into the team and just saying like dot value equals something else. Second thing is you can use read-only, which is built in for fields. You can use private setters. Then you can build, so this is like language level help. Then you can go on one step further and go into libraries. You can use something that's called builder pattern. If you ever used string builder is a builder pattern, which basically freezes an object. So if you have a really expensive build-up time, and then afterwards the object is kind of intact, then you can use the builder pattern. Then you have the immutable collections, which comes with the base class library in C#, or you can just switch to F# and get it for free because there actually you have to say you want a mutable code when you want to have mutable code. So ideally, we want our language to help us do this. However, if you use C# at all, you notice that some things are already immutable. For example, string, even though it's a class, it's immutable. Datetime is immutable. You cannot change the time. You can create a new time, which is different in relation to the old one, but the time itself cannot be changed. Also, anonymous types in link queries, they are also immutable. Value tuple, the new thing that came a year ago, so the language support for tuples, it's also immutable by default. And if you have for each loops, you cannot change the var part in it. And also, if you ever have a for each over a collection, if you change the collection, things break because you have the exception where you modified the collection, enumeration cannot continue. So there are some parts of the language which force you to think about immutability. So it's not really that alien if you think about it, because you've used it before. However, we need to talk about one thing. It's performance. I have a demo here, which basically does a very simple thing. So we have 3 types of code. One is classical. We have, I hope you can see this code. It's kind of the point. You have a list of integers, and then you add 1,000 elements in the list, right? You have the immutable list collection, which comes from the base class library, and you do the same. And you have immutable array, and you do the same. So it does the same thing, right? So if we run this code in release mode, it's going to take a while. Doing something excellent. So if you think about it, the code does the same thing. So if you were to go into your code base and replace all lists with immutable arrays, immutable lists, it will compile. If you look at the inner part, the for loop, nothing really changes. It's l.add, 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 right? It's kind of the same, but there are some performance penalties. Because if you want to guarantee immutability, you have to then jump to hoops to actually mutate something, because you have to create a copy of something. So you have 2 problems. You have the performance overhead, because you're doing something that you were not doing before, and you have the memory allocation overhead, because you're again creating copies of things, which kind of seems redundant in certain cases. Well, this will take a while. We're going to come back to it later. I actually have finished it before. If you look at the times here, you can see that immutable list is atrociously slow. It's almost 150 times slower than just using generic list, which is immutable. Also, you can see that immutable array is a slight improvement. It's twice as fast as the immutable list, but still, how much? 80 times slower than generic list. So you wouldn't just go into database and do like string replace and hope for the best. That doesn't make sense, because performance-wise, it's not the best thing. There are caveats. However, there are other improvements which you get, and now depending on your project, you have to decide: am I mining Bitcoin and I really care about performance, or am I doing complex business logic and I care about the ability to reason about code, testability, and actually that the code is correct? These things are actually far more important in everyday life than just pure performance. But beware that performance definitely suffers. I have posted links in slides so you can follow for more information about different types of things. For example, this is the blog post describing how F# is non-performant in certain regards. Also, if you look at the default, if you look at the blog post published by Microsoft themselves, comparing like when would you use certain collections, It's like if you're in C++ again, you have 4 operations, and then you pick one you don't like, and then based on that decision, you decide which one to go for. So you also need to know about your business case. What are you doing with data before you jump into immutability itself? Okay, so let's move on to the front-end world. Front-end, in this case, I mean client-side development. Originally, this topic was built around JavaScript, but it can be repurposed in C# as well. So typical development is using MVC. M is model, MV is view, C is controller, right? So you have this three-tier architecture where you basically pass data around, mutate stuff, and update the view. And the UI is typically state-driven, so it's a good candidate to see how immutability can help us in this regard. So how do we approach this? There are several cases, as mentioned before on the slide before. You can do patterns. You can decide to do things differently, like MVC is kind of pattern. You can use libraries that will protect you from doing something bad. Like if you're using C#, you're going to use Immutable collection. If you're in JavaScript world, you're going to use Immutable.js, which will protect you from actually modifying stuff. You can actually switch the entire language, and then you get it for free. Like as I said, it's quite popular nowadays to use functional programming languages, or you can just switch entire paradigms where you think completely different, even if you're leaving the confines of this mutable world. And lastly, infrastructure. I'm going to touch upon it at the last slides, but it's another layer where you say that when you compile code, it's done, and nothing changes, stuff like that. So what's our typical daily process when we're developing code? You write code, you compile it, you run it, and then you debug because it doesn't work. I mean, that's how I work, not sure about you. I call it debugger-driven development because the first thing I type is debugger, press F5, and then I stop at breakpoint, and F10, F10, F10. I just basically see why my code is not working the first time around, right? This is kind of bad because it slows you down. So ideally what we want is a data flow, because most of our business requirements are phrased as given this input or given this set of actions, this code will do something on that input, and then you will get an output. If you just break down any CRUD-based application, you say like, if I open this page, I expect to see a table of these things, I will click delete, the thing will go into the database, delete stuff, and the page will refresh, and voila, it's done. So you can simplify it if you squint a little bit to this input code output, and then in that case, this immutability will help. Let's see how. But first, let's talk about a little bit about TDD, because TDD will force you to do the same thing. Anybody here doing test-driven development or test-driven design? Very rarely. So TDD forces you to think in 3 steps: arrange, act, and assert. So you prepare your environment, you execute the function you want to do, and then you get a result. And then you compare if the result is expected or not. So this is what TDD does. How can we combine this paradigm, which has sense, with this data-driven approach and combine it with immutability in C#? It's kind of like a far reach. So let's go into the typical client-side application. It's easy, right, to write applications. You use some model that you deserialize from JSON, you write some UI, you bind things to UI, and then notify changes when something changes. When the user clicks a button, things are happening. If you ever done client-side development before React, basically, this is how it will look like. You would have a UI, which is HTML, XAML, WinForms, console application. You have a model which comes from database, JSON, whatever. And you have this internal loop of, I changed, you update. UI command has, for example, user clicks on a button. You update the model because you refetch or you change data, and recalculate the full name from the first name and last name. And then you update the UI, and this is like a vicious circle. This sounds nice. It's really simple. However, it gets complicated because we don't have apps built around one model and one UI, and that's it. We have complicated models because our applications basically are always trees of data that contain inner data that contain inner data. We call it encapsulation. I call it trees. So when you have a command saying, I updated something, which part? Maybe multiple parts. And if you ever use this paradigm in C#, you've seen the identify property changed. Has anybody used it? Identify property changed? Yeah, so you know what I'm talking about. So basically, you have this pattern, basically interface and the pattern in language, where if you put this interface onto an object, and if you correctly invoke property changed method, somebody else will know you have changed. So basically, to propagate change throughout the application, you have to signal it. You say, hi, I changed. Somebody on the other side, typically UI, will listen for change and update. Now, this, again, sounds really simple. For typical demo example, we have like one button and one text box, and you click a button and text box updates, voila, that's simple. But if you look at typical applications nowadays, it's never that simple. It's much, much more complicated. And also, if you have dependent events where you have like grids and you change one value in one cell and then the whole footer recalculates, it's a problem how to signal these events properly across the large infrastructure. I had this problem when I found out that weak event exists, and I was like, why would you have weak events if you have events in C#? What is weak about this one? And then I read about memory problems and events, and I realized that I never unregistered my events. It's easy to do event handler plus equals handler, right? But when do you unsubscribe? That's also a problem in large applications. And if you have used MVVM, this is actually really a nice depiction of MVVM. Like, this is how applications would look like. Count the number of all these arrows. These arrows basically mean that these two blocks of code interact in some way. As you can see, the number of these arrows grows exponentially with your application. That brings some kind of overhead. It's mental overhead. You need to know when you update something, what will change. You need to track cycles. If you worked with XAML-based applications, internal system actually tries to avoid cascading updates. If you worked with AngularJS, the original one, the one version, it has a serious problem with performance because it didn't properly handle these cascading updates. That's because the foundation is the observable pattern, which is basically this. I observe you changed, and it's all the way around. And Facebook had this problem because they have a complicated single-page application, let's be honest. They found out that all these arrows of cascading updates is really, really hard to track. It's really hard to reason about. And you would find something that's really interesting in this, and it's called a cycle. When you have one view updating one model, when one model is recalculated, updates another model, and so on and so on, you cannot see, it's really hard to see, but there might be a cycle. Cycle means deadlock. Deadlock means crash, and that's something you want to avoid. But you cannot know if you're a developer, you're working on your particular small component, you don't really see the big picture because that's the point. You see the small picture because that's how we divide work. But it can get complicated. So how to solve this? I'm going to talk about Redux pattern here, which is most applicable in React, but I'm going to apply it to C# as well. So let's change paradigm. Let's switch from this observer pattern, where everything observes everything else, and switch to immutability. So you have data, and you build UI on that data. Fine, that's the initial load. So you change data. Excellent. Where did you change? You create the copy. The UI still has the original data. How did you propagate change? How does the UI know that you changed something? And if something has changed, what has changed? Which parts of the applications should be updated? How do we introduce immutability in this typical simple observer pattern that we typically used? So we're going to switch things around and make so-called Unicycle data flow, where basically the first row is basically the initial load, the first load of the application, and then eternal cycle of the application that works. It's open and you do something with it. So if you look at the action, so what's the data? Is this store? That's the immutable part. It doesn't change, and based on that store, you create your view. You render your page. You render your application. When something changes, you basically, this is ignore. It's like a message bus. You change the store, you change the data, and then you rebuild entire UI. And that's basically it. So we to switch from this forest where you just emit events, I'm changed, who cares? If somebody cares, they will update themselves, I guess. You switch to this thing where you have a single source of truth or multiple single sources, depends. That defeats the point of single, I guess. So you have the data here on which the UI is based, and when you change data, you change the UI. How does that work? Let's look at typical example, because this is a real life code, right? Counters, you do counters every day. You have a single value inside. It's 0 by default. And when you want to change something, you do C value ++. Now, if you want to do this in Observable world, you have to implement kind of property change. In the setter, you need to implement property change dot invoke myself as I have changed. So if anybody cares, update the UI, because this by default doesn't emit change. And let's do it a little bit object-oriented. So you have the encapsulation, right? Okay, so this is a typical state of development before you introduce immutability. It's quite simple, right? You can reason with this. Except I apologize for the lowercase methods in C#. It's really atrocious. And let's switch to this thing. Now, this is quite a jump, right? But I'm going to walk you through it. The idea is that we have a store, and we store one number inside. And then, if you want to set the value, you can set it directly. If you want to increment it, you increment it by 1. But notice it's not plus plus. It's actually old state plus 1. So whatever had before, plus 1. If it's a minus action, then we decrease it. OK. This is the old code. So for comparison, if you look at it, it's inverted. It's instead of having methods, and if you've ever done some computer science investigation, you would know that every method in a class has a secret property called this, which basically is the data on which the methods operate. So basically, this is a method that accepts hidden property this, and this value plus plus. So it's kind of, if you squint, there are parallels. You have the constructor, you have the individual methods split as like a large switch statement. OK. How does it work? You start with the default value. You say, OK, by default it's 0, right? Then you dispatch action 5. It's kind of contrived example. Bear with me for a moment. It's going to get better. You set to 5, and then you assert it's 5. Yeah, it's 5. Then you set increase, increment, then it's 6. Then you set decrease, and then it's 5. OK, so is this OK? Do you want a real-world example, maybe? I hope you won't, because I have prepared it. Excellent. So in this case, I have a slightly more complicated object that's called class that's called a person, right? And the person has a name, and the person also likes to watch movies, and it has a list of favorite movies. So what do we want to do is, because it's really hard to build up code, let's start with this. So you have like a single property name, and then you initialize it in the constructor because it's kind of immutable, it's private, so nobody can change it except the person itself. And you have a fun method called withName that accepts a new name and creates a clone, mini-me basically, changes the name, and returns a clone. So if you had like 40 properties, you would have 40 methods with each, for each property. And if you were to use this, we have, let me just jump here, we have a store where we store this person, and whenever something changes, we're going to just print it to console so that we see things are actually changing. Okay, so we have a simple set of actions. We will create, basically load from database, a new person, it's John Smith. Then we're going to say, oh, your favorite movie is a Star Wars movie. I will not say which one, but it's definitely not the Phantom Menace. And then we're going to change the movie rating, because like it's IMDb copycat of an application. We're going to set the rating to 5 out of 5, not 10. OK, so let's run this code. Hopefully it compiles. Come on. Because this is the problem. Let me just uncomment this thing, because the idea is to increase the difficulty over time and then see how it is easy to do something like that. OK, so we have John Smith by default, and let's see how that came to be. So the store, wait, sorry, that's jumping. So store here has one person, right? By default, it's null. The default value for until C#8 comes, default value for class for reference types is null. So we have null inside. We subscribe, blah, 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 and then I say, OK, now we loaded the person that's called John Smith. So we want to change this inner value to John Smith. And this setPerson action is a funny small class, which basically just remembers data. It's really simple to serialize. That's the point. This is a simple class that's easy to serialize, load, and reason about, and track across the application. And then how do we apply changes? We have this function, which is a pure function, which means it doesn't have side effects. It gets some input, does something, returns an output. It has benefits. It's coming from a functional world. So given a current value of a person and then some kind of action, something has happened, you say, OK, so if an action was the setPerson action, this is the C#8 syntax, then we basically return this person. This basically means that this is the initialization. So once you get this action, what you act on it, you just set the internal value to person. OK. So let's say we want to add movies. Because you can see that in the output down here that nothing has changed for the movies, even though we have emitted actions. So let's introduce new fields. And let's change a constructor a little bit. So we're going to have a private list of movies, all the movies that a person likes. we're gonna expose towards the outer world read-only collection, not just if we expose the list, anybody can just say like movies.add, and we want to prevent other developers from accidentally modifying something that should be immutable. So it's read-only, right? And in the constructor we initialize it. Sounds simple, right? And so similarly to how we had the with name, we can have the with movies. Okay, let's handle this this second action, which is add favorite movie action, which basically has just a movie. So which movie you want to add favorites. Again, easy to serialize, easy to reason about, self-contained, long name, so it's quite kind of descriptive. Where are we handling this? We are handling this in the reducer. Okay, so we basically say, if we are adding a new movie to favorites, we basically say, let's create a new person with the old name, and then let's just append a new item to the previous list. This basically says like all the previous values union the new one, which basically means append. It looks a little bit complicated, right? That is the point and the problem as well. Okay. So again, you wanna implement the third action, change movie rating, which itself has the movie ID, which movie to rate, and the new rating, right? So you want to implement that as well. It's again easy to reason about. So how we're going to implement that method? We're going to comment this code. It says if we are changing the movie rating, we are creating a new person with an old name and all the other properties. But this time we're going to go through the list of movies. If we find this movie, we have to kind of do error handling as well. If we find the movie, then we create a copy of the old movie. So it's kind of all the way down, right? We get a copy of the old movie, but with the rating. And then otherwise, if it's just a normal movie, then you don't modify that one. Or if you want to do it with syntax, there's additional implementation where it's kind of so you take the existing person with movies, and then you go through all the movies, and you have the with rating. So it's kind of, if you look at it, there's a pattern here. Whenever you change a single property, there is a with method, and that's basically working all the way down. And if we run this code, you're gonna see that now it should work. Okay, so in the beginning we had John Smith, no favorites. Then he got a movie, Star Wars, with default rating, default for integer is 0. And then we rated it 5 stars. And if we, just for the kicks, we can implement rate 10. And if we run this method, you're gonna see that we're gonna have a fourth result 10. Okay, so this was kind of a trip to implement immutability in C#. As you can see, it is kind of painful. That is the problem. But there are benefits. I'm not sure if you got that benefit as I did before, but implementing these subparts was really, really easy, and it was kind of additive code. When I want to implement, for example, remove movie from collection, unbookmark basically, I create a new class, so I add code, don't modify the old code. I create a class that's called remove movie, and that it accepts an ID. And then I implement it as a switch inside this long switch kind of statement. This is basically pattern matching in C#. So I will just add new code. The idea is that you add code, you don't modify code. See what I did there? The old code is immutable. Kind of, it's a stretch. So the idea is also that if you have this function that takes a state, grabs a command, modifies it, it's really easy to unit test this as well. You can imagine, like, given the state of a user where it has, I don't know, 50 bookmarks, you can easily test a new method that does like calculate average rating for all movies or get my top 10 favorites. It's really easy to reason about this because all the parts were intentionally simple. The methods, the actions were simple POCO classes, which are easy to serialize, easy to pass along. It's basically DTO. The switch statement basically acts as if you had the methods that were named. You can imagine having a person class with literally a public method called change rating, right? So if you squint a little bit, it's known, but there is a pattern to the madness, and there is a lot of value to gain inside this. That was kind of real world solution. Less counters, more persons. So you can see it's kind of hard to do in C# because it wasn't meant to be this way. And there is a lot of boilerplate. Imagine that with name, that was short. But if I had 40 properties. Do I want to write 40 with methods? That's going to be a problem, right? And there's also performance issue because you're doing copying, and copying means that you allocate new memory, and allocations are expensive, right? But then again, all of these things are supposed to move a needle to your case if your case has other pros that can get from this thing. And luckily, the future of C# is that they're trying to help us in this regard. The C# in the past couple of years has implemented numerous functional concepts like pattern matching and tuples. And now they're working on thing they call record. So this thing here is a record. It's a struct. It's a pair. It has two values. You can imagine it's a person with string name and array of favorites. And this is the code you write. That's it. If you want to read more, there's a link. And it will generate this. It will generate a really, really nice code for you. And you can see that it has with method already generated for you. So the idea is that, yeah, in F# you have with method, it's built in the language, and in C# you don't, so you have to build it yourself, and it's error prone, it's repetitive, but it's coming to C#, so there is a good reason to think about it going forward, because it's going to be in the future very easy to use. Okay, so why would you do it? What's the point? I watched this awesome talk by Cheng Lu on the React Conf a couple years back. He was talking about powers of abstraction. It's kind of generic topic, and he said that, yeah, you can always do more in object-oriented languages, in Immutable. You can do more. Immutability slows you down. It reduces the things you can do. It just tells you you can copy it. That's basically it, right? And he says that it's not about potential power of doing more with mutability. It's about exploiting properties you gain by doing less. And by doing less, we basically said we will not use half of C# language features, because that's the point, right? Immutability is a constriction. You constrict yourself to subset of a language. So what do you get? If you look at this is actually now a real production code that we use in Xamarin application. This action is easy to serialize. You can notice that I cheated a little bit. It's no longer private. Because I do due diligence, I never modify unless I have a bug, and then I realize I have modified. So it's really easy to serialize, to save on disk. It's easy to log. And this is a real world example of how things can go bad. And if you want to go really wild, this is one single reducer. The point is not to read the code, point is to scroll through it, right? And that code is quite stable. It's incredibly stable. We have in this application, we had this tree structure. We had the application was for personal trainers. They had to track what they did in the gym, and they did a lot because it's weights, right? And you have to update all these different things, and managing that with updates and events and messages passing, it was annoying. And when we rebuilt it in this mutable fashion, it was kind of working from the get-go, because each piece was done individually, and each piece is by intention or by design. And because it's mutable, it's easy to test, easy to write, easy to reason. I mean, it's C#, so it can be simplified if you were doing it in F#. But if you squint and if you get accustomed to it, it's becoming really, really easy. Okay, so you might think, okay, so how efficient is this? When you create a copy of a large object, like you have person with 40 properties, and it has arrays, and arrays have their properties, and voila, and it stores all the way down. You might say, okay, so I want to change this small property at this end. I'm really going to make a copy of the entire structure just to change an integer, to change like an input field. Somebody's typing really fast, and you recreate the whole class hierarchy. Well, the point is you don't do that. There is this optimization that's been done, especially in the immutable languages themselves. Like if you're using F#, it's not really that slow. That's not the point. Actually, they're quite fast. The idea behind such languages that they are fast, like Lisp, Haskell, or Camel, similar. So what you do is you basically create. This is the old node, and this is the new node. So you reuse all the nodes that were created. And the bigger and the more complex the structure, the bigger the saving, because you're only creating copies when needed and only modifying when needed. So in that case, it's not really that inefficient. And if you have an array of 100 elements and create a new array with 99 elements intact and one is different, you reuse 99% of that array. The only thing that's new is the list itself, but list itself is rather small because it's pointing to all these other existing elements. I'm talking about linked list in this case. So yeah, what about real-world objects where things go really wild and nobody has an application with a button and a counter? That's always the typical demo example, but it doesn't scale. So what would you do in that case? You would actually, what we did, you would normalize data. You would avoid nested data structures. You basically simulate a database in memory, where you basically go to the objects, and all the child objects you extract in the top level and basically simplify a structure. It has additional benefits. It actually can lead to less memory overall, because if you have a JSON response of 100 elements, and each element, for example, blog posts and authors, the typical example, if you have a blog post with an author, and author is like ID, name, and maybe a link to profile, if there are 30 blog posts done by the same user, you're going to have 30 times the same sub-object. By normalizing data, you actually have one. It's one user that did the authoring. So in a way, this normalization can actually save memory in the long run, which is kind of like a nice side effect to this. So what do we get with all this? Because I promised that we're going to get so much more. You get replayability. Why? Because if you save those events, because the only thing that can change data is those like actions, you can replay any problem in your application. You can just basically reissue those events in a simulated environment, or if you want to save it from a real app and then execute later, it's possible. It's easy to test the application because everything is self-contained, everything is immutable. All these constraints help us narrow down the possible things that can change, and you always test for the things that can change. You have something that's really cool. It's time travel debugging. You can literally go back in time, because it basically means recreate up until a certain point the UI. You can do snapshot testing. You can say, okay, so after these 100 events, what's the current state? Save it. And then you can maybe later replay the same events and see if you get to the same state, because usually applications are more complex than having like simple events. So we want to do complicated scenarios. You can do fuzzy testing. You can create tests that basically randomize the inputs. If you have string, send null, send empty strings, send the long string. And you can do it really easy to test the boundaries of your business logic. And it maps to RPC really well, because RPC, remote procedure call style development, every action is basically an intent. And if you want some references, why would you do it in a client world? There is this project Fabulous that's basically F# inspired by F# framework inspired by Elm for building Xamarin Forms applications. That's a lot of buzzwords there. And also, if you want to do something with Immutable UI, you can see this cool library by Frank Kruger. And also, in the other non.NET world, you can see that Flutter and React Native are basically new frameworks that are built with immutability in mind. Basically, everything in the client world since React has moved towards this immutability, because there are really good reasons for immutability, especially as the project goes bigger and bigger and is basically need to scale it. Okay, so let's quickly jump over the backend, because I don't have a cool demos for that. They're too big. So backends, like client applications, are easy. You just write domain model, you write persistence layer, save it in Mongo, save it in Elasticsearch, whatever. You write business logic, that's easy, right? And then you handle incoming requests and map those domain models, details using maybe AutoMapper. That's easy, right? Well, not really, because if it was that easy, everybody would be doing it, right? That's how it usually the adage goes. We have different problems when you're building scalable web applications with thousands of requests per second. I happen to have never worked on such applications, so my experience is not that big in this regard. My applications were rather small and used by a less number of people, but you notice certain patterns over time. Things are difficult to reason about when everything can change, and whenever you pass something to a sub-function, you don't know if that sub-function is going to change property, is it going to save it, what are the side effects. The immutability will help you deal with those problems. So what paradigms can we apply by taking immutability in mind? So because typical backends are done using MVC, 3-tier, N-tier style architecture, and if we want to move away from that, so where do we go? Typical example is CQRS. I think there is a talk today about CQRS. There is also actor style development. It's, for example, akka.NET or akka in the Java world. You can easily build microservices. For example, Azure Service Fabric is a good example of this. Or you can even think about serverless as each immutable chunk. When we talk about immutable parts, you can still do one trick. You can cheat a little bit. You can say the part itself in its public interface surface is immutable, but internally it is mutable, because sometimes it's easier to basically just hide mutability from outside the world, because then it's contained. And typically when we talk about actors and we talk about serverless, we are doing that. We are hiding the complexity in the small chunks, which then interact And from outside the world, if you look at an architecture map, they appear to be mutable, even though internally they're not. I mean, even F# is running on a mutable machine, so it has internally it has to do internally something mutable. So immutability is just a facade, but it's a very useful one. Or you can do event sourcing. I'm not sure if anybody's doing event sourcing. Event sourcing is really the implementation of this, and the Redux, the example I've shown before, is actually a client-side implementation of event sourcing pattern. So what do we do in CQRS if we want to talk about immutability? The idea is that all the DTOs are now just simple DTOs that are easy to serialize, again, as before. And when we save stuff in database, the idea is that when combined with event sourcing, we just save those events. We don't change anything. We basically just store what has happened as a historical trace. It's like doing double bookkeeping. You basically double-entry bookkeeping. You just basically stored all the list of events that have happened, and at the end you recreate the current state by replaying all those things in memory. So immutability helps you go a long way with that, because otherwise you would have no capacity to do that if you were not doing immutability. So how would you typically do it? You separate your command layer from your query layer. In the query model, which is where you actually want to get data, in that layer you basically recreate the current snapshot from all these events that have happened in your system. And in the command model you actually change stuff, and each change is an hopefully atomic unit of change that changes something in the backend. Actors, as another way of doing it, as I said, actors can, from the outside world, appear to be mutable because they receive messages, they return response, which has lots of nice benefits, because when you have something that appears immutable, you can cache responses from it, because given the same input, it will give the same output. And by building something that's communication between such immutable parts, you gain a lot of these nice benefits that you wouldn't be able to gain through mutable development, where any piece of code can touch each other's part. We are now in our company doing, I didn't found it. So in our company, we are doing this reinvention of the data layer. The biggest problem we have, because it's an old application, we have 100 C# projects. We don't know when somebody changes something in database because things are not located properly. And this is a problem for example, if you want to implement webhooks, you want to know when something changes, so you want to emit event, which is useful from a business side perspective, because we don't have a centralized way of architecting stuff, because it's just traditional MVC style architecture where every controller can modify pretty much anything. Then you get what you paid for. You get that anyone can change anything, and there is no guarantees, which you would get had you followed something that's built on foundations of immutability. And as I said, with event sourcing, which is a paradigm shift in how we do things, we only store events. We don't store the state itself. And the state is basically derived from re-executing all these events that have happened before. So what happens when we start using immutability, regardless of is it like just a small library, is it the whole front end, or is it the entire back end, right? So the one thing that jumps to mind is it's easy to reason about. Why is it easy to reason about? If nothing changes, you have nothing to reason about. Like, this is a constant. Methods that are built on immutable data, when you apply functional principles, like you send in data, DTOs, simple plain old C# objects, and you get a response back. There are no side effects. It's easier to reason because all the logic is contained within the application, within the small code. You can easily test that more easily. If you apply this on a larger scale, you get something that's like a data model or pipeline architecture, which basically means that you can model your entire application in small boxes and say, like, this box does this one thing, it gets information here, it outputs information there. If you ever used promises in C#, or in JavaScript, that's basically that kind of style of development, where you basically pass something in and then it sends something out. It's really easy to reason about. It's really easy to test and develop, because everything's done in isolation, basically. One other thing that's maybe less, it's a bullet point, like threading, scaling, and ability to execute on a mass scale. That's less relevant for majority of applications that we typically do, but in certain cases where you want to parallelize your data flows, Immutability helps tremendously, because if there is nothing that can be changed between two different machines that are working on the same data, you can basically do it without locking. And that's what immutability helps you with. Like I said, I don't typically do such things. I just need one thread and maybe one background thread for downloading. But if you were to do something on a parallel scale, function languages with their immutability actually help. And also, if you want to do parallel development in C# without locks all over the place, you would go for immutability, because immutability tells you that different threads cannot change each other's state, or they cannot change the shared state. So if it's immutable, then it's just a number, right? And number 5 is immutable. You cannot like twist it to make it something else. It's always 5. Thus, the shared state between different threads when immutable helps machines basically work faster, which is a fun thing to think about. If you think about immutability on graphs, let's imagine you have like a 1,000,000 node graph. You want to do it on parallel machines, you have a copy of everything everywhere. It sounds unreasonable, but then again, if you have like 1,000 servers in a farm, they can do much more on 1,000 servers, regardless of the memory problems, than if you were like if you have a mutable model and you just have one thread accessing it. Okay, so the furthest point that we can go when applying immutability is applying it on our whole architecture layer. And that's where, for example, containers come in. Containers are a new trend where you basically keep all these small things immutable. Yeah, you build them, but that's the builder part, and then you freeze them, and then you're done. It's your pipeline now for deployment and building applications is founded upon this principle that you package your code, and that's it. There is no more updates to it. It's just a container. And I have a link on one of the previous slides by Martin Fowler. He talks about whole this bunch of patterns that are using immutability. Like if you have Phoenix framework built on top of Elixir, or Erlang. I think Campbell mentioned Erlang earlier. So all these languages were invented actually for companies that had scalability issues and needed some guarantees, and immutability came in and helped them have those guarantees. So one thing that we do in our company, we are using, this is like a small explanation of why would you do it. We have a large application on ASP.NET, which cannot be containerized because it's super old, it has VBScript and stuff like that. So instead of going for containers, we opted in for virtual machines, which is basically a fat container, I guess. And then for every deployment, we build this huge virtual machine. It's, like I said, a fat container. And that container is deployed in isolation. And if you think about it, before deploying code in every day, the image itself on which you deploy the code is always the same. It's immutable. Thus you get the guarantees. Nothing will break from day-to-day deployment. I'm not sure if you ever used web deploy. Web deploy is a technology in Visual Studio, basically for deploying web applications. It has this, when you're deploying for Visual Studio, it has this checkbox which says remove files before deployment. It's always turned off. I once got bit of it. So why would you have a checkbox to remove files before deployment? Why? Because it copies on top of previous thing. It's not immutable deployment. And I actually had the problem when I deployed an application on top of a previous application, and one DLL was from the old application, and things broke down in production because it was using reflection and crazy stuff like that. Because I didn't have a clean environment, because my target wasn't clean. So what we get with this kind of approach, we have, these are all VMs, and not in the I think Kubernetes cluster. And when you have a new version, this is basically new version, this is the old version, you basically spawn a copy of everything, and you can guarantee, because of immutability, that every node here is exactly the same as every other one, which gives you stability and gives you guarantees that you have you can do correct load balancing. Nothing is reused when you deploy again. So you're not deploying on top of on top of the old node. You can easily switch back if there is a regression because you haven't discarded the old stuff. If you deploy on over something, like if you overwrite stuff, you cannot undo overwriting because it's really hard to track what has changed enough. So this is immutability on a larger scale, where you basically want to guarantee that every change is atomic, that easily revertible, and easily discernible from something else. And if you have scaling in play, like we have in this case, you want to guarantee that every node is exactly the same as every other, because it can do stuff like load balancing, caching, and stuff like that. Okay, so the conclusion is to do less is to do more. To do less means use less mutability. And to get more means you can do more work, you're more productive, you get scaling for free, and you get predictable code. And with that, I have 9 seconds left, and I want to thank you for joining me for this wonderful afternoon. I hope you enjoyed the rest of the conference. If you want to ask questions, you have 2 seconds. Otherwise, you can find me in the experts area. So thank you.